evening and speak to you about a topic that is very close to my heart, Earth observation, in particular when it comes to greenhouse gas monitoring. Thanks Jochen for bringing me along to this. Okay, so what are we going to talk about? That's interesting. Okay, well, there's supposed to be a title on this slide. It's not shown for some reason. You see my name and a beautiful picture of a satellite. The title of this presentation is can we measure greenhouse gases from space, and how do we do that? I'll be talking to you about that. It's actually really nice to speak to an audience that is not working on this topic day in, day out. So I've tried to kind of simplify things. I enjoy writing about this also for more, let's say, a general interest audience. So here's two articles, one in Dutch and one in English, that if you're interested in the topic you can find more about it. Both of them are not for specialists in the field. So I work for TNO. I will not be speaking furthermore about TNO, but just for your information, so you know where I come from. TNO is a Dutch research organization. We are very active in the space domain. We have a few hundred people doing basically two things. We develop satellite instruments, so like real hardware that goes up there and does all kinds of measurements. We are in particular well known for doing atmospheric measurements. And the other thing we do is we utilize satellite data to basically generate useful information, typically for governments, the EU, but increasingly also for companies, and obviously we try to also make a scientific contribution with that. TNO is part of a wider ecosystem in the Netherlands that includes ESRON and the KNMI, the University of Delft, who have been working for a few decades on the development of Earth observation instruments that measure the composition of the Earth's atmosphere. So here you see a couple of famous missions that we've worked on, and the flight hardware that was developed in the Netherlands by TNO together with Airbus, who is like the industrial prime on these projects, with ESRON and KNMI. Now, the question is, using that heritage, can we take a look not just at the composition of the atmosphere, but also to look at concentrations? So not just how the atmosphere looks in general, but let's say the sources that cause the pollution that then disperses throughout the atmosphere. The answer is yes, and in my talk I'll basically show you how that is done. Jochen will then take a deep dive into what we do with that data, with a particular mission called Tango. Now, let's start at the beginning. We start with sunlight. Yes. Okay. So here we see planet Earth revolving. Around that fly satellites, in this case in a low Earth orbit, LEO orbit, 500 to 800 kilometers altitude. And basically what they do, they have cameras on board that basically measure reflected sunlight. So we have the sun, light goes to planet Earth and bounces back to the satellite. And what the instruments on board of satellite do, basically spectrometers. Now I know you're astronomers, so you're fairly familiar with spectrometry, I'm sure. But they're basically looking for absorption features in the light that they measure. Now how does that work? Here you see the impression of Anthropogenic, one of the satellites that was developed in the Netherlands, of which we'll see some examples in this presentation. Basically, let's see, is there a pointer here? Yeah. What basically the satellite does, it basically scans the Earth for a certain area, a rectangular area that we call a SWOT, that is divided into subsections, pixels, and the light that comes from that area, and that's not a 2D area, it's a three-dimensional column, is basically brought in view by the telescope, and it is then basically goes into the spectrometer, which usually uses a grating to show the spectrum, after which we can make analysis of these spectral features. Then the light is captured on a detector. So basically we have a telescope, spectrometer and the detector in electronics, equivalent to a normal camera system. You have the lens, that here. You have the body of a camera and you have a film that goes in it. I mean, very simplistically, that's how it works. Now, the result of that is basically a picture that gives you a concentration field. So in the slot, each of those pixels, you can calculate the amount of pollutants that is present in the atmosphere. Here I give you an example. This is the United States, and what is plotted in this figure is the amount of methane in the atmosphere. So methane, an important greenhouse gas, after CO2 the second most important greenhouse gas. And here you basically get a plot that shows you where there is a lot of methane in the atmosphere, red, and where there is less, yellow. And you see some white spots. That's areas where the measurements don't work because there's terrain issues that interfere with the satellite, or there's clouds, for example. So this is very useful stuff because it allows us to develop an understanding of the presence of certain gases in our atmosphere, being greenhouse gases or other. It doesn't tell us where those emissions are from. And for that we need instruments that are precise enough to basically show us plumes. Because when we know there's a plume, we know something is going up in the air. Here you see a map of Buenos Aires and surroundings, and here I've put a picture of the same instrument that was on the previous slides, Topoma, and it gives you a picture of the amount of methane in the atmosphere. Clearly you see here, so this is Buenos Aires, that there is a hotspot of methane there. Well, that's interesting to know. So apparently a lot of methane goes up into the air. How come? Methane is not released by cars and things like that, and it's not in big quantities, so there must be something. So Topoma, however, doesn't give you the spatial detail to really tell what is happening. There's other satellites we can use here. There is a satellite called GHGsat. The difference about them, we'll talk about it later. That allows you to really pinpoint to a certain location where there's a landfill that has a big emission of methane. And here you see plume-like features appearing. So this is how spectrometers help us to look at planet Earth and identify areas with emissions. If we look at greenhouse gases, there's two important species that you want to measure, CO2 and methane. For methane, currently we have a rapidly growing fleet of satellites that can measure that gas, including at sufficient precision to identify plumes. And we can roughly divide that into two categories. There's missions that have global coverage, so they give daily or every 3 days. They make a complete picture of planet Earth with sufficient spatial detail, typically in the multiple kilometer range, to see plumes and measure emissions. But these are very big plumes. We call them usually the super emitters. So that's really like the very big accidents in oil and gas facilities, the large landfills, things like that. But the good thing is they have global coverage. There's a second type of missions that are missions that can measure globally, but only make the actual measurement in smaller areas, typically tens of kilometers wide, in very high spatial detail. 100 meter scale, sometimes 50 meter scale. So these instruments have locally a much higher precision and they can measure smaller sources. One of the missions that we'll discuss later, Tango, is an example of such a targeted mission that looks at specific areas of interest. Now, for the Tango mission, we use an instrument that is developed in the Netherlands, and it was developed by TNO in partnership with ESRON and the KNMI, but the hardware is really, let's say, a TNO innovation, and it's actually an evolution of the instrument that I used in the first slide, Topoma. Topoma, fantastic Dutch instrument that makes global measurements, We've made a little brother of it that is much smaller, an order of magnitude smaller and cheaper, but still provides science-grade measurements. And that's very important because climate is something that is obviously very important. Global warming is a generational challenge. And unfortunately, we don't know a lot about emissions. We often will talk about that later. We're basically in need for much more data. And the instruments that we've been using to measure greenhouse gases have been very expensive in the past. Let's say order of magnitude 200 million euros. So that's a lot of money, and you only get to build them every, let's say, 10 years. This spectrolite instrument, thanks to miniaturization of technology, we've been able to make it smaller, and it only costs you 10 million for the first, maybe 3-4 million for the second model. So that's really much more affordable, and that's important for science, because if it's cheaper to produce, you can bring it in orbit faster and make available data faster. So what we're trying to do with this instrument is to really ramp up the amount of data that is available for emissions. The instrument was built. Here you see a prototype. The prototype measures nitrogen dioxide, as with methane. Nitrogen dioxide is important if you want to measure emissions, however. I think you will cover that, Johan. Here you see a campaign where we put this instrument under an aircraft and flew it over Berlin. And here you see the results of that, where in blue you have low concentrations and in yellow you have high concentrations. So clearly there's a plume here, and there happens to be a coal-fired power plant just here. So we know this instrument works. Now we're going to put it in orbit in the next coming years. Now, what makes this instrument important? I think they're more different from other instruments. Two things I want to say about that. It's the amount of spatial detail it can see. So here you have a map of the Netherlands, and in that is plotted the typical, the SWOT sizes of some of the satellite missions that were in my previous slide. Here you see Tropoma, the one I used for Buenos Aires, you remember, where you could see that there was something happening, but not quite where. This shows you why, because if you would have to look at Amsterdam, it's only a few pixels of that instrument. Now, if you go to Tango, there's a very tiny white dot here, and that's more the size of the pixel we're going to get. So this enormous amount of spatial detail will allow us to look at emissions in a higher precision. The other important thing about the instrument is its optical performance. And that you can give a whole presentation about how these instruments work and why they perform the way they do. This is with the limited time I have not the place, but I show here in let's say exploded view of this instrument and how the light is traveling through the instrument, through the telescope, through the spectrometer, the slit, into the detector. As you can see, this instrument uses mirrors to basically bounce the light through the instrument. And if you want to measure something from 500 kilometers above, that's very difficult. So the fact that we can measure those gases is already quite an achievement. If you want to measure plumes, these tiny features down on the ground, your main challenge is the amount of light. Basically, you don't get a lot of light, so you have a low signal. So the signal to noise ratio for the instrument builders in the room is a big challenge. So it means you have to be very efficient with the light. So you should not lose too much light in the instrument. And one of the main innovations that underpins this instrument, and most of the famous Dutch instruments that have been built in the past decades here, are freeform mirrors. And this is an example of such a mirror. So this is an optical element that we use to put the light in place. And it's not like, a typical piece of optics that you expect, a spherical transparent lens. It's made of metal. And the surface of these mirrors is extremely tightly controlled. So in TNO, we make lenses that have surfaces with a roughness in the nanometer scale. So nanometer scale, that is like for mechanical engineers. I'm a mechanical engineer. It's a background that's unbelievable. That's almost like atomic molecular level precision. Because these lenses are so precise, we can make them very efficient with the light. Because they have such a awkward shape, we call that a freeform shape. One of these mirrors can replace 3 traditional optical elements, and you basically cut out the losses that each optical element has in the system, and you make the instrument more efficient. So by putting this mirror in instead of 3 lenses, you can save 20% on your optical performance. And that, for 500 kilometers, can be the difference between seeing something and knowing what you see. So it's really optical innovations like this that Netherlands is quite famous for, that allow us to make these ultra-compact instruments that measure emissions. So around this whole set of technologies, we've developed a very exciting mission called Tango. And enough, I would say, about the hardware and all the stuff that's inside it. Jochen will tell you something much more important, what we will do with it. So that's it from my end. Do we do questions now or later? Yeah. Okay, so if you have any questions, let me know.
Questions for Anton?
I think you're working mostly infrared ranges, isn't it?
No, it depends. So for the greenhouse gases, yes. There's a couple of wavebands in the infrared where we can measure methane and CO2. But other gases like nitrogen dioxide, which we also use in the Tango mission, they're in the visible light. Other gases that we won't be talking about today, like ammonia, they're more in the thermal infrared, so that's even larger wavelengths. So it really depends on the gas.
Well, apart from this one, obviously, are there any other missions that you're kind of excited about in the near future? What you can do?
Thanks. So right now, the Dutch Earth observation sector, if you will, is really focused on Tango. That is, let's say, our big national project that we want to realize in the coming years. The money for that is in principle allocated, but I'll spare you all the politics and the complexities how you go from money that is in principle allocated to a flying mission. So we'll be quite busy with that. Meanwhile, we are indeed already looking at the next challenge. One of them is measuring ammonia. I already mentioned it. It's only relevant for the Netherlands because we have the stikstofcrisis in Dutch. So ammonia emissions from farms in Netherlands, but also in Germany, in France, north of Italy. And we're now developing a new type of interferometric instrument to measure ammonia plumes. What we're also doing is we're developing an instrument that's potentially an order of magnitude preciser than what we're presenting here today, to basically push the detection threshold of greenhouse gas emissions even further down. That's a nice development we do together with Sterrenwacht in Leiden, with Frans Snik and some colleagues, also in the interferometric concept, just to give you an idea.
You showed a picture of the comparison for the resolution of Tango and previous instruments like
yeah.
How does the SWOT compare? So what is the coverage and does it have any influence in the science that you do?
That's a very good one. Anthropogenic has a SWOT of 1600 kilometers, something like that, Jochen? 2000 kilometers. And the methane product is roughly 7 by 7 kilometers in pixel. For 2000 kilometers, that's quite a nice granularity, but it's still crude at the local scale. Tango has a swath of 30 kilometers, so that's a very small part, and it has pixels of 300 meters roughly. You can still optimize that a bit, you can make it 100, you can make it 400, so that's a little bit how we optimize the optics.
And does this have an influence in the science that you do with them, or is irrelevant?
Does that have influence on the science? Is that your question?
Yes.
Yes, well, obviously. I think Jochen's presentation will think very nicely over that. Yeah. And so this is only a bit about the general background and the technology, and the science will be dealt with by Jochen. But yeah, I think an obvious difference is that, and that's not even in the science, instruments like Tango, but also some of its colleague missions, because Tango is not alone. Tango, like Carbon Mapper and GHG-SAT and Methane SAT, are missions that all have a relatively small swath and a small pixel that do these local measurements. These missions are basically capacity limited, in the sense that you can only measure a certain amount of locations per day worldwide, even though they can measure everywhere. Whereas Anthropogenic, CO2M, that's an important ESA mission coming up that will push down the detection threshold for greenhouse gases significantly. They provide you a global picture almost daily, which is fantastic for scientists because you don't need to schedule your satellite, you can look at historic events, you can look at locations where you before you didn't know something was happening, but they are detection threshold limited. So yeah, they're different animals, if you will, and clearly it influences how you use them. More questions? Yeah.
Is there any time delay? How big is the time delay between the measurements and that the policymakers can act in the pollutants, can catch the pollutants in this?
Well, that's a good point. Right now, all these missions are science missions. So policymakers are still either unaware of them, I'm sorry to say, or they are trying to figure out how to use them. So I think for the policymakers, it really depends on how well the case is presented to them. I mean, from a technical point of view, it depends on the mission. In missions like Tango, we aim to have the data available within 1 or 2 days. So that could go really quick, and in principle you can do it within a day. It's basically limited by the amount of stations you put on Earth to transmit the data from the satellite back. And that's again mostly driven by money. If you have enough money, you can use a couple of them and you can do it even within parts of days. The big challenge is to go make the step from basically science to policy in that. And a lot of good things are happening for that right now. Yeah.
Is it very obvious that we as humans are the biggest contributor to the CO2 and methane emissions?
Oh, I leave that question to a real scientist. Yes. Confirmed.
You showed high precision optics made of metal, but does it shrink and expand with temperature?
Yes, it does. Yeah.
And it's a big problem, or you engineer it the way it needs to be?
Yeah, it's absolutely, yeah, it's metal. The nice thing about metal is you can predict quite nicely how it behaves. Well, as long as it's still linear. So the differences shouldn't be too big. So making these mirrors that are very precise is one thing. To mount them in an instrument in a very precise way is just as difficult. Otherwise, why make a very accurate element? And then keeping it accurate after launch, under which enormous shocks are put on the instrument, enormous thermal gradients, and then you put it in orbit with one side of the satellite heated up and the other one cold. And that's the art of satellite instrument making. So we spend a lot of time and energy modeling and testing to make sure that it does not impact the measurements. So yes, it has an impact, and yes, we can deal with it. Actually, I was showing Jochen just before this presentation a picture of a structural thermal model for Tango that we are already now putting in a lab to deal with all these thermal gradients. So cool stuff. At least if you're a mechanical engineer like me, then you think it's cool stuff.
Did you have a question there?
Then is it possible and or planned to take these kind of instruments to other planets like Mars and Venus?
To where?
Mars and Venus.
Yes, it is happening. Yeah, there are missions to other planets that look at the composition of the atmosphere. Absolutely. Yeah. Yeah, we are sometimes involved in that, a little bit. I wish we could do it more, but yeah, you can spend your money only once.
Any other questions?
I see someone there in the event.
Is the straightening spectrometers mostly on pinpointing the hotspots or on estimating the total emissions?
I would say save that question until you've seen Jochen's presentation. And if it's not answered, then ask Jochen, but I think you will see some very cool stuff about that.
Someone else had a question there? Yeah.
Yeah. Is it possible to determine at which height of the atmosphere something is absorbed? Or
If something is absorbed higher in the atmosphere,
Not with that mission.
no.
There are other missions working with that.
Any final question? May I ask what's the lifetime of these missions?
Yeah, that really depends. So if you have the classic missions, they're usually the big ones, so the €200 million or more expensive costing. They have, let's say, 8 years, 6 to 8 years is what they're designed for. But they are so overqualified that usually they last 10 years, 12 years, or even longer. Next week we're celebrating that OMI, the instrument, has orbited planet Earth 100,000 times and made 9 billion measurements. It is unbelievable. So that mission really lived much longer than we expected. Tango will be on a CubeSat, so the satellite of Tango will be this size, and they're cheaper, and they will not live that long. We expect, let's say, 4 years, if we're lucky 5, if we're not so lucky 3. But yeah, it comes at a lower price. So when the first one burns in the atmosphere, they completely burn down, so there's no debris. The second one should be in orbit already.
Okay, with that, let's thank our speaker Anton again.